Saki, how you doing? Saki, how you doing? Hi, Javier. Hi, Javier.
Doing great.
Okay.
Today's better.
I understand. Believe me, it's a pain that doesn't go away.
Yeah.
Okay.
Sometimes I think about her and then stare at.
You understand why I had to say what I did, though.
Yeah, I understand it.
Okay.
So I did my best.
Guys, just thank you, Suki. Guys, if you are asking to have a report, results, or a post lab, if you're asking for that to extend the time, I'm probably not going to do it for you if it's your first miss, because that's what the drop grade is for, guys. The drop grade is for emergencies, and you have to decide when you want to use that. Is that fair, guys?
Yeah.
Yep.
I'm sorry, that's why we allow the drop grade. So please don't even ask. If it's your first one, don't ask. If it's your second one, then yeah, it's going to hurt you. So I'll be a little more lenient on that. All right. Is that fair enough, guys?
Yeah.
Okay. Let's see. I got 9 of you in here, and there's supposed to be 13. This is one you shouldn't miss, guys. This is really one that you shouldn't miss, because the concepts behind this, half of the lab's really easy. Half of it is super, super easy. The other half is challenging, to say the least, okay? So, anybody have any questions about last week's lab? Last week's lab, everybody should do pretty well on it. Except for Aditya. Make sure I got your message, Aditya.
Yes.
I got your message. Yes, it's going to hurt. Yes, it's going to be penalized, but it's not going to be devastating, okay?
Okay, thank you.
So I'm kind of treading here for a couple minutes to see if I get anybody else in. But the second half of this is going to be very difficult to wrap your head around. First part is not, okay? So go ahead, Faye.
In the like lab section for this, it says that watch the video. It's the first link?
Okay.
I'm sorry, to get the
I'll share the screen. I'll
okay.
share the screen, okay? Are you seeing the screen, Faye?
Yes.
Okay, I'm going to go to the course content.
Well, I watched the video and they just didn't really get a clear like picture or like a standstill on the for the first double displacement, when you're supposed to say how milky it is and how the particles are like accumulating at the bottom, like those observations.
Okay, there is one, Faye. There is one that you have to be very, very careful. The precipitate is not that great, but it is there. I will grant you that, Faye.
Well, I'm thinking of the one you're talking about. He added stuff to make it more visible, but that's the only one, right? And the other ones don't look like it, don't have it.
There's only one that I can recall. Okay, I do know the one reaction you're talking about, Faye. And there's only one that I've had students kind of like do this on. Okay.
Mm-hmm.
And literally speaking, in a face-to-face class, I have the ability to look at your results as you're doing it. And see what your observations are. And I can say, hey, I think you know how to do that one again. Unfortunately, I don't have that ability here. I don't know what else to tell you, Faye.
Okay, so just make a really good, educated guess.
If you want to, Faye, you can email me and ask me whether you're whether your conclusions are okay.
Okay, yeah,
Be
okay.
very specific. I don't want you guys emailing, well, what are all 16 reactions? Okay. Be very specific when you ask the question, because, well, let me do it this way. I know there's one funky one. You're allowed to ask me one result. Fair enough?
Yeah, that's fair.
Okay. Good enough. You saw where to get the results though, right, Faye?
Yeah, and I know which one you're talking about, which is funky.
And by the way, Faye, the one that is funky should be a precipitate.
Yeah.
He had to add more stuff to it to make it go. So
Yeah.
that one should be a precipitate.
Okay. Well, in the lab, it wants us to do color, degree of cloudiness, size of particles, and settling tendencies. Is that that's specific enough?
That's not part of the, to be honest with you, just call it a precipitate or not.
Oh, okay, great. Thank you.
All right. Literally speaking, if you want to get into all that other happy horse shit, you can, because there are nuances that make something look different than something else. Like the precipitate of calcium with iodate may look a little different than the precipitate of magnesium. And by the way, I'm just throwing this out of my head. I don't have this stuff memorized. Are you kind of understanding what I'm saying, Faye?
Thank you, Professor.
No problem. I would just go precipitate, no. If you do that, you should have enough information to answer the questions. Okay?
Okay, thank you.
All right, let's get to it, guys. I want to see if I want to change the colors. I'm going to reload this and hopefully it'll come back up. I did something for humor yesterday and my class didn't get it. So as a consequence, I had to change the colors. So I am changing them back to the funny ones, or at least what I call them funny. Where am I at? 10:45. And it's not to be funny, it's just to keep things consistent. That's the only reason I'm doing this. Okay, we're going to stop share. And hopefully we're going to share the screen again, and hopefully it's going to be up there. Yay. All right. As I said, guys, first half of the lab is going to be very, very easy. Okay. And what you are doing here is you have 4 known solutions. The 4 known solutions are going to deliver the anion. Okay. The first solution gives you sodium. Actually, yeah, in the directions, it's sodium sulfate. Second known anion is sodium carbonate. Third one is sodium oxalate. Fourth one is sodium iodate. So are you noticing the consistency of the sodium, guys? Are you noticing that? So the reason you are doing that is you want to make sure that the cation of the 4 known solutions isn't the thing that's causing the precipitation. Does that make sense to you? Does that make sense, guys? So what the chemicals that are known are the sulfate, carbonate, oxalate, iodate. That's what you know. Okay. Then you have a series of 4 alkaline earth metals. Yours are going to be magnesium, strontium, calcium, and barium. All right. And the magnesium, calcium, strontium, and barium are all going to be the chloride salts. Now, if I mix the sodium from the known mixtures that are delivering the anions, and I mix the chloride from the known things that are delivering the alkaline earth, sodium and chloride, that's salt. Is the salt going to precipitate? NaCl.
Yes.
Salt, NaCl. Salt is not going to precipitate. You've dissolved salt in water forever, guys. Sodium and chloride, that's not going to react to cause a precipitate. The reason we're doing that is to make sure that you know it's not the sodium or the chloride that's causing the precipitate. It is actually the alkaline earth and these individual anions. Eventually, what you are doing is you're going to determine what your unknown alkaline earth metal is. So what I did was I found up 4 new alkaline earth metals: doctorium, mean dogium, disgustium, and questionium. And I mixed those 4 new alkaline earth metals with sulfate, carbonate, oxalate, and iodate. Now, the way you perform this experiment, you have a plastic dish, and the plastic dish usually has 12 depressions in it. So what you do is you put it on a dark surface and you add an equal volume of the SO4 and you add an equal volume of the doctorium. If you see a white precipitate, you have a reaction. The best way to record that is in a table like you're seeing here, like one that is in your notes. And what I would normally do when I'm doing this, I would fill the first depression with sulfate, second depression with carbonate, third with oxalate, fourth with iodate. Then I would take my chloride and I would take it, squirt it into each one of those wells. And I would look to see whether I got a white precipitate. When I did not get a precipitate for sulfate, carbonate, oxalate, but I did for iodate. Okay, next four wells. Again, I put sulfate, carbonate, oxalate, and iodate in it. But this time, instead of adding I'm adding And when I added to each of the 4, for sulfate, I got a precipitate. Carbonate, I got a precipitate. Oxalate, I did not. I got a precipitate with iodate. Same thing. At I put my last 4 depressions, I put sulfate, carbonate, oxalate, and iodate, and I add to each one of those. In this instance, I got a precipitate in the carbonate, and I got a precipitate in the iodate. I got no reactions for sulfate and oxalate. When I did the I had, by the way, at this point, I filled all 12 wells. I got to go and wash out my depression dish. So I get the depression dish that's clean, fill 4 wells with sulfate, carbonate, oxalate, and iodate, and precipitates in all 4 of them. Now, I'm going to put my sulfate, carbonate, oxalate, and iodate in 4 new wells. Now I'm going to add my unknown. And my unknown did not react with sulfate, carbonate, oxalate, but it did with iodate. Now, guys, it becomes a simple matter of matching my unknown to one of the 4 possibilities. And I'm going to look at the reactions. My unknown did not react with sulfate. Y did. Have I eliminated Y? Have I eliminated Y, guys? Come on, I know it's 9:30 in the morning.
Yes.
Okay, have I eliminated
Yes.
Okay, so now it comes down to UG or AH. So I look at my carbonate results. My carbonate precipitated with UG, did not with carbonate. So even just from the first 2 tests, I can tell that my unknown is what, guys?
Ah.
We can check that with the last two tests. My sample did not react with oxalate, but it did precipitate with iodate. So I am fairly confident at this point that my unknown is Ah. Again, with the precipitation, we are identifying the cation. And that's another thing I probably need to point out to you. When you're given your unknown, you're given a solution, a clear solution in a test tube. Now you have to understand that you have two unknowns here. You have the cation that you're going to identify, and you have the anion. One salt, two unknowns. So you've done all these tests, and literally speaking, you feel fairly confident. Precipitations are going to identify the cations. Anybody have any questions on that?
So when you look at your chart, whichever one has a P with no, could you just quickly say it again?
Okay, basically you're matching it. You look at your unknown versus Y. You got three contradictions here. Does that make sense, Faye?
And the
I'm sorry, was
CO3.
that you that was asking?
Yeah.
Okay. Do you see, look, for Y, you got to precipitate with sulfate, carbonate, and oxalate. You did not with your unknown. Can it possibly be Y?
Okay.
All right, you're comparing it to UG. UG, you got a no reaction and a precipitate, which is consistent with the unknown, but your carbonate is not. So can it be UG?
No.
All right, you have conflicts for GUR for the sulfate, carbonate, the sulfate and the carbonate. Can it be GUR?
No.
Now you compare it with Ah. You're getting no reactions for three of them, a precipitate in the fourth. Are all the results consistent, Faye?
Oh yes, they're the same as the bottom line, right?
Yes. You're
Okay.
comparing the bottom line with each one of the four.
Okay, thank you.
And I cannot emphasize this enough, guys. The results section here is basically you get 100% or a 0 on this. If anybody, for this part, if anybody says that your cation is sulfate, carbonate, oxalate, or iodate, you got a 0, guys, because those are your known solutions. You're testing other knowns, and your unknown has to have, for this particular portion, your unknown, you're identifying one of the alkaline earths. Does that make sense, ladies and gentlemen? Any questions on the precipitation portion of this? The cation identification. Everybody fairly well gets that like that. Any questions on this part?
No.
Okay. Now, is there anybody in the class that has not had the chem reactions lecture yet? By that, I mean identification, single replacement, double replacement, combustion, those kind of things. Is there anybody that has not had that? Please speak up now. Okay, so everybody knows what a single displacement reaction is. But what you probably don't know, or it's been thrown way back in your mind, is that single replacement reactions are also can be identified by another name. And that is an oxidation reduction reaction. Now, in an oxidation reduction reaction, you have two things that are happening. One thing is losing electrons, the other thing is gaining electrons. Loss of electrons is oxidation, gain of electrons is reduction. And there are two mnemonics. You can either use Leo goes GUR, loss of electrons, oxidation, GUR, gain of electrons, reduction. If you don't like that, use oil rig. Oxidation is loss of electrons, reduction is gain of electrons. That will help you determine what's the oxidation and what's the reduction. The other important thing here is you cannot have an oxidation without a reduction. We can't lose electrons to the atmosphere and just have them floating around. If they're out there, they're going to be grabbed by something. So whatever's going to grab them is going to be the reduction, and whatever gives them up is the oxidation. Now, I have a reaction. Most of you are used to seeing single replacement reactions. You recognize them by seeing a neutral metal mixed with an ionic salt. Does this look familiar to you all? Max, shake your head. Thank you. And really, what happens in a single replacement reaction, the metal displaces the cation of the ionic salt and makes a new compound. The cation then becomes neutralized. And this happens because in this particular instance, magnesium is losing its 2 electrons to become the ionic cation and delivering 2 electrons. Those 2 electrons are accepted by the copper. And so the copper, which was an ion, accepts the electrons, and it now becomes neutralized. Now, Max, you're my flunky, okay? Ooh, he just gave me a dirty look. Max, you're my flunky. I'm a drug lord in Colombia, okay? And I have my kilo of cocaine, and I'm just entering MIA, which is an appropriate analogy for Miami, missing in action. So I'm just entering MIA airport, and I see my Mr. Customs man up there. What am I going to do with my kilo of cocaine? Am I going to try and carry it through, or am I going to force it on you?
Definitely force it on me.
So I have some electrons. If I'm a chemical, I have some electrons and I have more power. If I'm more active, I have more power. I can force those electrons on you. If I force those electrons on you, then I become ionic. And if you were ionic, you now become neutralized. The more active substance ends up ionic. If we're talking about metals, the more active substance gets oxidized, loses its electrons to become the cation. The less active substance accepts those electrons, it becomes neutralized, and it has gained the electrons. Does that make sense, guys? Does that make sense?
Yeah.
All right.
Yeah,
it does.
The important thing to remember, more active ends up ionic. That's the first rule behind all of this. More active ends up ionic, because I'm about to flip the tables on you.
So wait, go back real quick. So the magnesium is more active than the copper and the copper
Yes.
sulfate?
Yes. If the
Okay.
reaction, Max, if the reaction goes, okay? Say I threw a magnesium. Magnesium's a silver compound. So, and copper sulfate is a blue solution. Say I threw the magnesium in there and I noticed brown stuff forming and the solution started to lose its color. Did a reaction occur, Max?
Yeah.
Then I know that the magnesium was creating magnesium sulfate, and I know that the magnesium is becoming an ion, magnesium more active than copper. That's the whole logic we're going here.
So because it was more active, it oxidized?
Yes.
And then, okay. All right. That makes sense.
Yes. Now I'm going to throw this switches on you because I'm going to talk about halogens and halides. Remember, loss of electrons is oxidation, gain of electrons is reduction. Okay? So if I mix potassium bromide with chlorine, all right, if you have your periodic tables, look at them. If you're not, you're going to have to bear with me for my memory. The halogens start with fluorine, next one down, chlorine, bromine, iodine, correct?
Yep.
Which one of those elements is the most electronegative?
I think it's fluorine.
Amazingly enough, guys, all that stuff you learned way back then, it comes back to haunt you. Yes, you're absolutely correct. Fluorine is the most electronegative. What is the least electronegative?
One like all the way down.
Iodine. Iodine is going to be the least electronegative. So between fluorine and iodine, which one's going to want electrons more?
Fluorine.
Between chlorine and iodide, which one's going to want electrons more?
Fluorine.
Fluorine.
Between chlorine and bromine.
Chlorine.
All right. Now, I mix neutral chlorine, and neutral chlorine exists as a diatomic molecule, Cl2. I mix neutral chlorine in water with a solution of potassium bromide. I'm putting bromide that has a negative charge next to chlorine. Which one's going to want the electrons more, chlorine or bromine?
Fluorine.
So the chlorine goes from being a neutral thing to being an ionic thing. It's grabbing the electrons from bromine. And the bromine, subsequently, since it's lost its electrons, will become neutralized as the halogen. And by the way, guys, I've got to tell you, if you see the halogen as something with the subscript 2, that is the halogen. That's the neutral one. That's how that substance appears in nature. If you see the element with a negative charge by it, that is the halide. That is the substance that has the charge on it. Okay? So if we mix these two things together, KBr and Cl, by your normal logical deduction, a reaction occurs and we get Cl minus plus Br2. Again, the reaction occurred. The chlorine, which is more active, is in the ionic state. Have I said anything that sounds stupid yet? Okay, again, that emphasizes our first rule. The more active substance ends up ionic. Now, the second rule we have, if the forward reaction goes, the reverse reaction will not. In other words, if I add my reactants and I make products, if I then turn that and I say, okay, I'm going to take my products, mix them together and see what happens. If the forward reaction goes, if you mix the reaction and the reaction occurs, then if you mix the products together, no reaction will occur. And this makes sense because if I'm looking at this in the forward direction, chlorine is more active than bromine. So chlorine's going to grab the electrons from the bromine to make the Cl minus. Now, if I reverse it, chlorine or chloride is more electronegative than bromine. Bromine's not strong enough to pull those electrons off the chlorine. If bromine's not strong enough, no reaction occurs. So either one of these, by using either one of these reactions, I can tell you that chlorine is more active than bromine. In the first, it's because it did react. I reacted the halide with the halogen, and I got the halogen to change into the halide. I got a reaction. The first reaction is indicating that chlorine is more active than the bromine. When I put the bromine as the halogen and react it with the chlorine as the halide, I got no reaction. This is because chlorine's more active. It's already ionic. It's not going to lose its electrons. Again, have I said anything stupid yet? Anybody confused at this point? Thank you, Max. Thank you, Max. You made me laugh. Are we good to this point, ladies and gentlemen?
Yeah.
All right.
Looks good to me.
All right. Now, in the process, we're talking about the first reaction. Bromine loses electrons to become Br2 because all the halogens have to exist as diatomics. If it loses electrons, it is oxidation. Chlorine, on the other hand, gained the electrons. That is reduction. All right, now, the basic concept of what we're doing in this lab to identify the halides. If you have known halogen in water and you add hexanes to it, hexanes is an organic compound. It's an organic compound that will favorably extract out the halogen. When it extracts out the halogen, different halogens make different colors when they're in the hexanes. Only the halogen gets extracted into the hexanes, the halides do not. So literally speaking, when we're looking at this reaction, we're only looking for the color in the hexanes. Does that make sense to you guys?
Yeah.
No.
Okay. Do you accept the fact if I have a halide in water, the halide is going to be more soluble in the water than it is in the oil-like hexane?
A halide is
Halide is
a mix
the,
between a metal and a halogen.
it's an ionic compound. Yes.
Okay.
It's a mixture between a metal and a halogen. If you put those in water, the halides will never extract into the hexanes. Okay?
Okay.
On the other hand, halogens, you got one Cl with another Cl. This is an entirely covalent bond, non-polar. The oil-like substance is also non-polar. So you got a non-polar molecule, it's going to be favorably extracted into the hexanes. Does that make sense to you? Who's asking the question here?
Max.
Okay, Max, does that make sense to you?
No, I'm sorry, but maybe if we go on, I'll continue to.
All right, let me, all right, to extract into water, water's polar, Max. Like dissolves like. So if water is polar, it's going to want something that has charges on it. Ionic compounds have charges in it. Okay? So the water is going to dissolve the ionic compound because the ionic compound has charges on it. Hexane is like oil. It is non-polar.
Oh, okay, that makes sense. I thought you said that the ionic compound would not be
I said the ionic would not dissolve in the hexanes.
hexane. Okay, never mind. I get it.
Okay. You sure you're okay, Max?
Yeah, I thought at first you said it wouldn't be in the water. I was like, why?
No, it won't be in the hexane. Now, the thing that happens when the halides get extracted into the hexanes, they have different colors. So we're only looking for the color in the hexane layer. Okay? So when we're doing anion testing, I mix Br minus with Cl2. Do we expect the reaction? Is chlorine more electronegative than bromine?
Yes.
Yeah.
Okay, if chlorine is more electronegative than bromine, then we convert all of the Cl2 to Cl minus. It doesn't go into the hexane. The Br minus gets converted to Br2. we should get the Br2 color in the hexane. Does that make sense to you?
Mhm.
Now, let's go to the second reaction. We have Cl minus, the halide, mixing with I2. Do we expect a reaction here?
Yeah.
Is chlorine more electronegative than I2, Max?
Yes, sir.
So, should chlorine give up its electrons to I2?
Certainly.
It's more electronegative, Max. If it's
Oh.
more electronegative, it's going to want to hold on to those electrons. That makes sense to you, Max?
Okay. So if I2 came before it, like if it was I2 plus Cl negative,
If I was dealing with F2, say, if Cl minus plus F2,
oh,
I would get a reaction because
so what?
F2,
So if it was, oh, okay.
the higher you go in the periodic table, the more likely that element is going to have a negative charge on it. Okay, Max?
Okay.
So
So what
if
if it
I'm-
was like Cl2 plus I negative?
Minus?
Yeah,
Well, you tell me.
still no reaction.
No, Cl2 is more electronegative. Right now, as Cl2, it has no charge. When compared to I2, it's going to want to have the charge, right?
Uh-huh.
So it's going to want to have the charge. So if I have Cl2 plus I minus, I'm going to have a reaction because the Cl2 is going to want to be charged. By the
Okay.
way, I'm sorry, guys. I've got a test going on at the same time. So as a consequence, I'm getting a lot of calls probably. Okay. Can you hold on 1 second?
Yeah.
If I get a call from somebody about the test that they can't get on, let me know. I'm so sorry, guys. What happens is I'm doing a test and you guys know the problems with honor lock. So if somebody comes with a problem, I may have to get out of here real quick. Okay.
That's fine.
All right. Getting back to this, Max, do you understand? The more electronegative element is going to want the charge. Does that
Yeah.
make sense to you? So if I
Yeah, it's
have
just when it's like diatomic, I guess that's when.
when it's diatomic, it's neutral, no charge.
Oh, okay.
So if
Oh,
I
yeah.
have if I have Cl minus with I2, Max.
Oh, because that's how they exist, is because they
Yes.
wouldn't be able, okay, as an atom, they wouldn't be able to exist without being diatomic. Okay.
Correct. Correct. Okay, Max. So I
Yeah.
have Cl minus plus I2. Is Cl more electronegative than I2?
Yes.
Yes, it is. So it's already charged. Is it going to want to give up its electrons?
No.
No. So do we expect a reaction in this?
No.
All right. Now there should not be a reaction. Correct. Now you got to think. I didn't get a reaction. So what should be in the hexane layer?
Like that purple.
I2. The I2 should be in the hexane layer because the I2 is still there. I didn't react it. So I should get the I2 color, which, as you said, Max, is purple. Other
Okay.
than Max, have I totally confused anybody yet? Come on, give me your questions, guys.
That makes sense to me.
All right, now, oh crap.
Be
It
fine.
changed. I'm gonna have to go with this. I used chartreuse, periwinkle, and carnation.
Chartreuse.
All right. So we're going to have to deal with the plain colors. This is a sexist joke, and it is because I was playing on the fact that most males do not know colors. Right, Max?
I don't know chartreuse because of the I think it's like a commercial now. I can't remember what it is. But that's the only reason I know that color now.
Yes.
I know periwinkle.
Periwinkle is green and carnation is pink. Doesn't matter. I was trying to make a joke there. So we have 3 chemicals. We have AS2, acinine, which is a foolish element. We have BF2, be fine, a meaty element. And we have AN, alienine, a foreign element. Come on, it took me a long time to think of these guys.
Those are good. I really like that. Especially
All right.
be fine.
So if we have AS2, that is going to extract into hexanes. I get a purple color. If I have BF2, that extracts in hexanes, but I get a green color. If I have AN2, that extracts into hexanes, but I get a pink color. Okay, because of the fact these are nonpolar compounds, they're all going to extract into hexanes, and when they do, they give me different colors. We're on a firm basis there then, huh?
Yeah.
Remember, only AS2, BF2, and AN give the colors. AS minus, BF minus, and AN minus do not give colors. Remember, the more active element is ionic. Whether it stays ionic from no reaction or whether it goes from being neutral to ionic because there is a reaction. What we're going to do is we're going to mix the ion with the neutral compound. We're going to mix them up. They're both in water. Then we're going to add hexanes to it to see what color I get. Whatever color I get will determine whether I've had a reaction or not. Are you with me yet?
Yes.
Yes.
Yeah.
All right. I mix AN minus with BF2 and I get a green color. Apparently I didn't change all of them. And I get a green color. Okay. AN minus to BF2 green. Which species does the green indicate?
The BF.
BF2, right? Let's make sure we say it as the halogen, okay? That means I have BF2, okay? Faye, did I have a reaction?
I would say no, because
No,
it's still BF2.
it's still BF2, so I had no reaction. All right, now here's the jump in logic. If I had no reaction here, what is more active, AN minus or BF2?
BF2. What?
BF2.
How is that not right?
Wait, it's not.
Is it
The question
AN2?
is, what is more active? The BF2 stayed, right?
Yes.
The
The BF2 stayed as BF2, right?
Yes.
yes.
Okay, now, was the BF powerful enough to grab the electrons off the AN?
Oh, because it was so powerful. Okay. So yeah, AN. AN's more active because of
AN
that
is
logic.
more active. All right, let's go through the logic process here again, guys. I mixed AN minus and BF2. I got green. Because green indicates that the BF2 was extracted into the hexanes, I did not get a reaction. That meant BF2 did not react with the AN. Since BF2 did not react with the AN is more electronegative than BF2, AN is more active than BF2.
Okay,
Right.
makes sense.
Come on, come at me, guys.
No, that makes sense now.
Yeah.
So we're dealing with this. I don't know if I put a slide there or not. Are you seeing something?
Yeah, did I get a reaction?
Okay, so AN minus is more powerful than BF2. We got that, right?
One minus is still a minus, right? And it didn't give up any of its electrons?
Correct, correct. Okay,
Yes.
keep that in mind. I mix BF minus with AS2 and I get a green color. Blast it. This is what happens when I do things. When I do
There
things
we
in
go.
general.
All right, I mix BF minus with AS2. I get a green color. What species does green indicate?
BF.
BF what?
It should be
Minus.
BF minus.
Oh,
B-
no. What, BF2 is a green color.
Remember, the halides do not extract into the hexanes. So make sure you got your species right. Green color indicates what compound?
BF2?
Did I have a reaction?
Yes.
So if I had a reaction, AS2 went to making AS minus. What is
Yeah.
more active, AS or BF?
BF2?
BF minus.
What did I make? If I made a green color, I made BF2, right, guys?
Yeah.
I made BF2. What else did I make?
Did
Remember, one goes to neutral, the other one's going to go to negative.
You made
If
AS minus?
I made AS minus. So I went from a neutral compound. Was AS powerful enough to grab the electrons from BF?
Yes.
it was.
AS was powerful enough to grab the electrons from BF to make AS minus and BF2. So AS was more powerful than the BF, AS more active than BF.
because it took BF's electrons.
Correct, correct. And subsequently made the BF2 that we noticed, that we observed. Now, from these first two slides, you know that AS is more powerful than BF, AS is more active than BF. And we know that the AN minus is more powerful than BF. So what is the least active of my elements?
BF.
AN is more active than BF, and AS is more active than BF. What is the least active compound?
BF.
BF is.
BF, yes.
BF is. I might have gotten lost in the logic there myself there for a second, guys. Now, I have to determine what is more active between AS and AN. So I'm going to mix AS minus and AS2. I get a pink color. Did I have a reaction?
Yes, because the AS2 took the electrons from AN minus, because now AN is AN2.
All right. Now, AS took the electrons from AN. What is more active, AS or AN?
AS2 is more
Yes.
active because it took them.
AS2 is
Still
more
confused on that. I don't
active.
get it.
Max,
No, I get the logic. I would have said the same thing as I think Faye said that, but I just don't get if an ion changes the color of a compound, then why is the compound more active than the ion?
okay, Max, let's talk in terms of halides versus halogens, okay? I know it's tough, but you got to start thinking that way. Now, try and word your question in those terms. Remember, the halide is the charged compound. The halogen is the neutral compound. Now try and ask your question.
Ask my, so the halide,
You're saying if the halide causes a change, you mix the halide and the halogen together and you get a change of color, you can't understand why the halide is not more powerful than the halogen.
yeah,
Okay? That's because you're getting that change in color.
oh wait, the neutrality of the compound, okay. Yeah.
Okay,
all right.
guys, to try and explain what Max just said there, the neutral compound is what gets extracted into the hexanes. So if I change the color, AS2, you're expecting purple. If I don't get purple, if I get pink instead, that means AS2 is not what's getting extracted in the hexanes. It is the AN2. So I get a reaction. Does that simplify it a little bit, Max?
Yeah,
So if I'm dealing with, gave those 3 different scenarios. If I'm going with the overall activity series, AS is more active than AN. We just determined from that last reaction. And we determined that BF is the least active. I'm here, guys. You're not going to have me when you're not going to have me at 10:30 next Wednesday night. What do you got, guys? Any questions?
let's look through the stuff.
So with the chart, that's what we have to do is like look at every reaction and just do like a greater than less than thing.
Yep.
For the part 2 chart single displacement, where we do like no reaction and we write down the colors to figure out.
For the part two, you're going to write down the colors, and basically for the part 2 part, you're going to compare the colors. Okay. I'll show you the chart in a second, Faye. Okay.
Okay. Yeah.
All right. Now, there's something that I disagree with Dr. Musgrave about, and that is he does not mix the BF minus with the BF2. He does not mix the AS minus with the AS2 and the AN minus with the AN. He does not mix those. The problem is he is assuming no reaction through all 3 of these, right?
Yeah.
And what he does with the experiment is he extracts the BF2 into the hexanes directly. He extracts the AS2 into the hexanes directly and the AN2 into the hexanes directly. The problem with that is that the colors change a little bit. When you add BF minus to BF2, you don't get the same color as you would if you just put the BF2 in the hexanes. It is a little bit different. It's a little bit funky. So when I do this test, I make you do the reactions. Understand, when I'm putting BF minus with BF2, I'm not getting a reaction. There's no reaction. So whatever is in the hexane layer is going to be what the color of BF2 is. I can't have a reaction because what would BF minus turn into? Will turn into BF2. I've got nothing to react there, guys. AS minus would turn into AS2. It's already there. AN minus would turn into AN2. Again, it's already there. I get no reaction. But I am recording the colors anyway because the colors vary a little bit if I add BF minus to BF2, it varies a little bit. So when I'm doing this, I'm going to add BF minus. I'm going to have test tubes. I'm going to add a small amount of BF2 and a larger amount of BF minus. I'm going to add a small amount of AS2 and a larger amount of BF minus. Small amount of AN2, larger amount of BF minus. These are the colors I get. All right. Now, remember, I said I got no reaction for this. This means this is the color of the BF2 in the hexanes. What do I have in the hexanes for AS2 and AN2?
Is it AS2
The
and
same color?
AN2?
Do I have the same color in each one of them?
Yeah.
If I have
Yes.
the same color in each one of them, then isn't the same compound in the hexanes?
Yeah.
And that compound is the BF2. Does that make sense to you?
Yeah. Does that mean that both AS2 and AN2 are strong, more, they want electrons more than the BF minus?
No,
More
because remember, I'm reacting BF minus with the AS2. And I got a reaction. I made BF2. So did the AS want the electrons more than the BF?
Yes.
So I
Because
got a
you made
reaction. I got a reaction for this one. I got a reaction for this one. So both AS and AN are more active than the BF2.
Yeah, that makes sense. But
All
not
right.
more active than BF minus.
Well, BF minus,
I can't remember the colors either.
AS2 reacts with BF minus. So I made AS minus. AN2 reacted with the BF minus. So I made AN minus. Both this one and this one grabbed electrons off the BF. So both AS and AN are more active than the BF. I know Max's head is doing this right now.
If you're comparing it from like the x-axis or the x of the y-axis kind of thing, like the side and then the top, why are you saying AS2 is more active than BF2 if
Okay,
we're mixing BF minus? I'm
I'm mixing BF minus with the AS2,
yeah.
right? What is AS2's color? Remember, the color of BF2 is this one. The
Mhm.
color of AS2 is this one. The color of AN2 is this one. AS2 gives a chartreuse color in hexanes. AN2 gives a carnation color in hexanes. So I got a periwinkle color. This meant that I have BF2 in this one and I have BF2 in this one. Understand, I'm mixing BF minus with AS2. Out of that, I got a color for BF2. That is a periwinkle. When I mixed AN2 with BF minus, I also got the color for BF2. That meant I had a reaction. If I had a reaction, then AS2 was more active than the BF minus. AN2 was more active than the BF minus. Does that make sense, Faye?
Yeah, I guess I'm just trying to think about it like writing out the chemical reaction. And you're just, because you're just saying that.
Let's go on to the next one, okay?
Okay.
All right. Now, I mix AS minus with AS2. I got a chartreuse color. So that is truly the color of AS2 in the hexanes. All right. When I mixed AS minus with BF2, I still got the BF2 color. Did I have a reaction?
No.
No, I did not. I am getting the BF2 color. So when I mix AS minus with BF2, I did not get a reaction. AS minus wanted to keep its electrons. So AS minus is more active than the BF2, which agrees with this result. Remember, I changed this from AS2, which was neutral, to AS minus to get the BF2. That also says that AS minus is more active than BF. So both of these two agree with one another. All right. I mix AS minus with AN2. I get a different color. I get the AN2 color. Did I have a reaction?
No, because it stayed carnation.
No, it didn't stay. Remember, if I expect to get an AS, I'm sorry, wait a second. You're right, Max. I'm starting to confuse myself now. You're absolutely right. If I mixed AS minus and AN2 and I got a chartreuse color, that would have meant I was getting the AS2 color. I would not have had a reaction, but I did. I got a change of color. I got a change in color. This meant that the AN2 was converted to, or the AN2 stayed as AN2. So it is more active than the AS minus.
Okay, so AS minus with BF2 is no reaction because BF2 stayed its color.
Yes,
And then AS minus to AS2, that's
the same thing.
no reaction too.
That's no reaction. That is the true color of AS2.
Okay, and then it's no reaction across the board.
Correct.
Okay,
Absolutely correct, because the AN2 stayed its color.
all right, let's try AN negative. So
It reacts with BF2. Did I get a reaction?
no.
No, I did not get a reaction because the color is still the BF2 color.
However, with AS2, you did get a reaction because AS2 is chartreuse and you got carnation, which is the color from AN negative. And then another reaction. Oh, no reaction. Right?
Max, I think you're getting it. I think
Yeah.
you're getting it because
Okay.
everything you just, that's why I didn't interrupt you. Everything you just said was dead on.
Okay. I would just
All
hope
right.
everyone else gets it too.
Guys, if you're not getting this, yell out at me.
Can I just reiterate
Go
like
ahead.
what we were trying to, so if we mix the negative, the like the AS with the AN2, and that's the AN2 color, right? Carnation. That means that there was no reaction because the AN2 is in the hexane layer, but if there
Well-
was the AS color, AS negative would be in the hexane layer if there was a reaction.
Correct. Absolutely correct, Faye.
The way
Okay.
that I'm thinking about it is that we're starting with the compounds up top, and then we're putting the ions into it. So if we're starting with the compound's color and it doesn't change, then there's no reaction because it stayed the color that the compound is. But if we look at like AN negative with AS2, we know that AN is
You're right.
Harry
Keep on going.
is
AS should be chartreuse.
chartreuse, yeah. So since the AN, when we put the AN into the AS2, it changed from chartreuse to carnation, then we had a reaction.
Absolutely. Absolutely. Is that making sense to you all? All right. Now, We have done all of our knowns. We've mixed the BF with the BF2, AS2, and mixed the AS minus with all three of them, the AN minus with all three of them. Now, what we're going to do is we're going to take our unknown and we're going to add a little bit of BF2 to one test tube, a little bit to AS2 to a second test tube, a little bit of AN2 to a third test tube. And we're going to add more unknown to each one of those. We're going to mix them up. Then we're going to add hexanes to it. Now, just like we match the things for the precipitation reaction, we're going to match the same things now. So if you were to make an observation here, what would you say your unknown is?
Be AS minus.
Anybody have anything against that?
No.
No.
I got the same reactions when I added BF2, AS2, and with my unknown as I did to AS minus. So I have AS minus as my unknown choice. I'm hearing a lot from Max and Faye. Can I have a
I
little
don't know
bit
if my
of
voice is quiet or not.
Samir?
Yes.
Are you understanding this?
Yes. Well, at least mostly I am. I understand how you find the unknown.
That's 90% of it. Okay. Finding the unknown is 90% of this. This other part, the other logic part of it, you're going to have to deal with in the post-lab questions. The results for this, super easy. The trouble with super easy results section is it's either going to be 100% or a 0. That means if you get the answer right, you get the 100%. If you don't, it's going to be a 0. Not quite a 0, but fairly much, all right? Just keep that in mind. Now, the results section is going to ask you, the first question is going to ask you, what was your cation? Remember, for the cation, you are listing one of 4 choices: magnesium, calcium, barium, strontium. Those are your 4 choices. Okay? Now, the second question is going to be, describe how you determined your answer. I do not want a simple answer of, well, my results match my unknown. That tells me absolutely nothing. What I need you to do is I need you to tell me the specific reactions. My unknown precipitated with carbonate and iodate and did not precipitate with sulfate or oxalate. This matched my unknown whatever. Period. That's all you have to, one sentence, guys. That's all I'm asking. All right. Then you're going to get asked to identify the halide. Okay. My unknown halide, all right, that's the first question. Second question is going to be, describe how you determine your answer. My unknown halide extracted purple into hexanes when treated Cl2, Bl2, I2. This matched my known something. If you just say matched my known, if you just say matched my known for those 2 questions, you're going to lose half the points. All I'm asking for you to do is add one sentence to that. Do I have everybody's understanding there?
So just state the colors and the reactions.
Yes, I need you to state the specific reactions, and you can do it as simply as I did it right here. Okay, Faye?
Okay, thank you.
All right.
Well, first, I don't want to interrupt, but I just need to leave right now. And
Okay,
if I
Saki.
understand after
Saki,
I'll email to you, or I will ask Crossman. Is that okay?
this is important. Okay, Saki?
Yeah.
I've given you the results of the halides.
Okay.
Okay. I've given you that because literally speaking, guys, that video, look through the video and you'll see what I'm talking about. The video is confusing. So I've given you the halide observations. That's the last slide of the slideshow.
And then we can watch this lecture, right?
You can rewatch it. Yes,
Okay, good.
I am recording it.
Okay, so I will, if not, like I will make sure one more time. Get the-
Saki, the only thing is I go through in a few minutes through the results and through the post lab.
Mhm.
If you have questions when you're doing it, give me a call, okay?
Okay, thank you so much. I'm so sorry.
No problem. Guys, this is the slideshow. Would you agree with my original synopsis of this? First part's really easy. Second part is involving thinking. Would you agree with that, guys?
Yeah.
Anybody totally out in left field?
I'm pretty good now.
Okay, let's go. I'm sorry, I gotta get out of here to go to there, stop share. Don't yawn, Max, it's
Hey, I did a lot of work
It's
this
con-
class.
it's contagious. Yeah, let's see, is this what I want? Crap, I got two of them. Yeah, I'm in the right one. Okay. This one, you are going to have to look at the videos to get the results, especially of the cations. All right, and we're in the determination of a why did that do that? Okay. Results. This is going to be quick. It's just as I described it. Start quiz. This one, definitely, there's only going to be one chance to it, okay? First question. Order of solubility. Now be careful about this because Dr. Musgrave does this all the time, okay? He switches most to least and least to most. So you got to be careful and read the question. 1 is going to be the most soluble, 4 is going to be the least soluble. What you're going to do is you're going to look at the chart you make. That chart, the compound in which you've written most precipitates or most reactions, that will be the least soluble, guys. The one which has the most P's on it will be the least soluble because those cations have caused the most things to precipitate out, make the solid. If it makes the solid, then it is least soluble. Does that make sense, guys?
Yeah.
Yes.
And honestly, what happens is all the time, I get this and I have the exact opposite. It's either from you're not reading this correctly and you just go, oh, 1 should be the least soluble. That's my most logic thing. But again, 1 is going to be the most soluble, 4 is the least soluble. And the second thing, again, this is a logic thing. You're looking at the precipitates and you're going to look at that and say, oh, well, it reacted the most, it must be the most soluble. No, it's the exact opposite. If it reacts to make the precipitate, that precipitate makes it less soluble. Have I just confused that issue, guys?
No, that makes sense.
Yes.
All right. Second question, rank the halogens in terms of least active to most active. Remember, the substance that ends up ionic is the most active. Get a free 10 points there. Pick a number. All right. Describe in detail how you determine the identity of your unknown cation. Guys, I want that sentence in there. My substance precipitated with sulfate and iodate, did not precipitate with sulfate and oxalate. This matched my unknown. That's all you have to say. But you have to do at least that. If you just say something like unknown cation reactions were the same as my known strontium, therefore it is strontium. That won't work. I need the specific reactions there. Unknown cation. Describe the, how you got the unknown anion. My sample extracted purple with all three halogens into hexanes. This matched iodides reactions. Therefore, I had iodide. And that's it, guys. Questions on that?
Can you repeat that sentence for question 6?
It's on the PowerPoint. And the PowerPoint will be uploaded, okay? Second thing. We're gonna go through the post lab. Good God, I'm in here for an hour and a half. Okay. Post lab. Preview. I gotta move this thing. Don't worry, my secretary is handling that call. And she's gonna, I'm gonna get yelled at. Okay, now this is gonna explain why I went through all that bullshit. Okay. All elements, all the halogens are diatomic molecular species. Their melting points are given. All right, anybody know what room temperature is in Kelvin?
273.
That's-
Some teachers
no,
make you
that's-
do the 2.
That's standard temperature. That's at 0 degrees centigrade. Room
Oh,
temperature is about 25 centigrade. So Kelvin, room temperature is 298.
Oh, okay.
What it's giving you is the melting points. If it's above 298, is it going to exist as a liquid or a solid?
Oh, liquid?
Yeah,
If it's a, if your melting point is above 298, it is going to be, I'm sorry. If your melting point is above 298, that's room temperature, remember? Above 298, you're above melting point. Now, let me ask you this question. If you're at 5 degrees, do you have ice or water?
Fahrenheit or
degrees centigrade.
Celsius?
What? Celsius. 5 degrees Celsius. Do you have water or ice?
Water.
Ice.
Because
Okay.
isn't 0 degrees freezing?
Exactly. So if you're above 290, I'm sorry, if you're above 298, you're at room temperature. It's telling you that it takes 457 degrees K to make iodine melt. Right?
Yeah.
So what are you expecting at 9? Are you expecting at 9 to melt at a higher temperature than iodine or a lower? Look at the trend. Fluorine melts at 85, chlorine 239, bromine 332, iodine 457. Are you expecting at 9s to be higher or lower than iodine?
What's at 9?
At 9, if you look at the periodic table, the one right below iodine is at astatine.
Oh,
Sorry.
acetone.
Higher.
Sorry, astatine. Sorry,
So we have to use our periodic table and find a placement and then see where it fits into the placement.
yeah, well, you tell me, where's astatine fit in the placement?
Well, it should be a.
It's a
How do you
higher
melt a halogen?
point
It's a
than all.
halogen. Where is it in relation to all of the rest of them?
Lower.
Lower. Okay. What's the trend? As you
Get
go
higher
down the chart,
temperature.
higher temperature. So you're expecting astatine to be a higher melting point than iodine or a lower melting point?
Higher.
It should be a higher melting point.
All right. If it's a higher melting point, is that above 298?
Yeah.
Yes.
So
It should be a
It's
I
gotta
don't
solid.
know if it'll
be-
be a liquid or if it'll be a. It'll probably be a liquid.
it takes more than 457 degrees to make iodine into a liquid. You're only at 298. What is iodine going to be?
Solid.
So
Yeah.
what are you expecting astatine to be?
A solid.
I'm not answering that question,
Right.
but
right.
that's the logic you're using. Now, if fluorine exists as F2, chlorine exists as Cl2, bromine exists as Br2, what are you expecting At to exist as?
AT2.
I'm not answering that. Okay, second question. Again, this is something like I went over in the PowerPoint. I went through this, remember, with the green, pink, and purple colors? You're gonna
Yeah.
have to pick one, either B or C. One of them is more active. Pick which one it is. This one. This gives you the colors, and you got to choose whether C is more active than A. Again, it's that logic thing that I went through with the PowerPoint. Again, asking, is C more active than B? That's all those three questions are. You're going to have to read through the description of what happens, and then you have to determine, is C more active than B? And he gives you a hint there. Then he gives you a whole scenario, and you have to tell me what the activity series is. This question, you have to develop a experiment that will identify the salt that is present in your unknown. And it gives you a choice of different procedures there. As I said, most of you are going to score great on the results. This is a whole logic thing. Guys, this is the whole, if you've ever thought, why in the hell are they ever making me take chemistry? If I'm going on to be a doctor and I'll never have to know anything more about chemistry again in my life. This is the reason you're taking chemistry right here. You're learning to critically think in a technical field. And this is the demonstration of that. Got nothing for you guys. It's been an hour and a half. I'm sure you're as tired as I am at this point. Any questions before we go, guys?
Oh, yeah, Professor, can I ask you a question about the recordings? Do you
Yes,
know
John.
where we can you show us where to find the record?
Absolutely. Okay,
Thank you.
Trin. All right, I'm gonna have to go. Course content. All right, I gotta take it all the way down. Down here, you're gonna see something called Zoom meetings. Click on it, then you gotta go all the way back up. Click on the site, and what it'll load is it will load a Word document. Then once you load the Word document, this is not going to come up because of the fact that hit Control, left click, and you're not going to be able to see it, but it will, I promise you it will load. Or actually what happens is there's a button that gets populated in the top toolbar. Click on the button. I don't even know if you guys are seeing this. Are you?
Yeah.
You are seeing it?
Yeah.
Yep.
So that's how you access the PowerPoints, Trend.
Okay, gotcha.
And this will be loaded up. I'll start it. I have to do something before I start it, but actually I have to walk the dog, then I have to do something and then start it. But after that, it will be loaded by 5 o'clock today for sure. Unless I
Alright,
run
sounds
into
good.
a problem.
All right, no rush.
Anything else, ladies and gentlemen? If that's it, I'm sure you're as tired as I am.
Thanks, Professor.
Thank
Take
you.
care, guys. Take care.
Have a good one.
Yeah.
Have a good day.
Take care.
By the
Have
way,
a great
this is,
spring break.
take care. You have a great spring break too. I'm having an operation.
Good luck, Professor.
Thank you. I'll be fine. I'm going to be fine, guys. That's what my spring break's going to be about.
Please update us
I will.
if you can.
I will, guys. I will.
All right.
Bye, Javier. James. You there, James? James. James. James, if you don't talk to me now, I'm marking you absent because I can't have you log in and then leave. That shows me you're not here. You're just logging in.